Dauzier, and he'll be giving a talk entitled Temperature-Based Inputs for Molecular Reservoir Computers. So Nicolas, you can take it away.
Hello everyone, so thank you for the introduction. So I'm Nicolas, I'm a PhD student at the University of Tokyo, and today I'm going to talk to you about temperature-based input for molecular reservoir computers. So why are we interested in such reservoir computers? So the reason is because we want to make molecular programs for swarms for Alife. So why we are interested in swarms of molecular robots? Because if you're using molecular robots, you can make many robots. So it's not crazy to think you can make 1 million to 1 billion robots, but it is quite hard to make a controller for such robots. So if you're interested in this topic, we did the tutorial at the beginning of the week. You might want to look at it. But so just to sum up on what we concluded on this tutorial is that you can use chemical reaction networks, and the one we use DNA reactions to make such controllers, but they have one quality and one default. So it's kind of easy or okay to tune the weights when you have such a chemical network, but it's hard to test many different topologies. So to solve this problem, we use reservoir computing. Why is that? Is because if you're using reservoir computing, you don't need to change all the topology of your system to get different behavior. So you can, most of the layers of your network or have a fixed topology, and you just need to tune the weights at the output layer. So that's what we're interested in. And what I'm going to present today is a predator-prey oscillator done with DNA that is used as a reservoir. And I'm going to show you how by inputting different temperature profiles, we can really control the oscillations of our oscillator. And then we monitor the concentration of DNA by fluorescence, and we input it into a single layer perceptron to predict what was the input temperature. So just the outline of my talk. So first I'm going to present a bit into more detail what is exactly the PEN DNA Toolbox predator-prey oscillator that we use. Then I'm going to show you how we showed that we can control the oscillations with temperature. And then in the last part, I'm going to show you the results of reservoir implementation. So first about the PEN DNA Toolbox predator-prey oscillator. So this predator-prey oscillator is made out of 3 DNA strands. So the first strand here is the grass. Here you have the rabbit, and here you have the fox. And if you look at the network, what happens is that the grass enables the rabbit to reproduce, and then the fox uses the rabbit to reproduce. So it eats the rabbit. And we have 3 kind of reactions. So the first one is the prey growth. So from grass plus rabbit, you get grass plus 2 rabbits. You have the predation. So the fox uses 1 rabbit to make another fox. So it eats the fox and reproduce. And then you have the natural death, or decay, is just the molecules, so the DNA molecules that are destroyed. And if you put all these in a test tube, what happens is that you have oscillations. You have a phase where first you have the growth, the prey growth, and then when you have a lot of rabbits, fox are very happy and they eat all the rabbits, so they grow very fast, and then you have no more rabbits, so the fox cannot reproduce anymore, and so you have just the natural death of the fox, and then the rabbit can grow again, and etc. And that's why you have oscillations. So how do we make this reaction work? We use enzymes and the PEN Toolbox enzymes framework. So the first enzyme is the polymerase. So this enzyme, when it sees this kind of half double-stranded, half single-stranded DNA, it just extends the single-stranded part to obtain a nice, fully double-stranded DNA. So you polymerize this part of DNA on the template. The nick is when you have a specific sequence here in the middle, it just knows it needs to cut, and it cuts, and so it means when you combine both from a black input that comes here and connects, you polymerize the output, and then you cut and you recover the green one. And then the exonuclease just destroys. And today we're going to focus mostly on this part, the exonuclease, and how we can use it for our system. So in detail for the DNA sequence, what happens for the pre-growth is that the rabbit binds to the grass, it is extended, then the nickase come into play. And so an extended rabbit is basically two rabbits that are connected to each other. And then you have the nickase that comes and you cut and you recover your initial rabbit plus one. So you get exponential growth. The predation, so a fox is like an extended rabbit. And because you have complementary sequences, the rabbit binds to the fox, it is extended, but there is no site for the nickase to cut, so it stays like that. And what happens is that you create a new fox. So basically a rabbit with an extra head is a fox. And then you have the decay where polymerized strands are just destroyed into bits. And how do we monitor all this content, all that's happening in the tube? So we use fluorescence. So the first thing is we have a fluorescent dye on the grass, and the fluorescence of this dye depends on if the grass is double-stranded like this, or if it's if it's double-stranded in this other position with a rabbit connected to it. And the fluorescence is far smaller when you have a rabbit. So if you look at the negative peaks of the fluorescence, they're proportional to the concentration of rabbits. Whereas we also added another molecule that just binds to DNA and whose fluorescence is proportional to the global concentration of rabbits and foxes into our solution. So basically, by looking at this fluorescence, you're able to see how the concentrations of the system vary. So now, how do we actually control these oscillations? So the idea is that if you put your oscillator at a normal temperature, around 40 degrees, you have nice oscillations. But if you increase the temperature, you have something weird happening here, like it doesn't oscillate. And it starts somehow, but the oscillations are very small. And why do we have this? And the reason is because the exonuclease, so the enzyme that we use, loves high temperature. So when you increase the temperature, the activity increases a lot. So here I'm going to give you two examples. So at the beginning, you just put a specific concentration of rabbits, for instance, and you get the enzyme destroy them. And you see that at low temperature, it takes a rather long time. But the more you increase the temperature, it's very fast. And that's true for both rabbit and foxes. So basically, by increasing the temperature, you increase the exonuclease activity. And we can see this in this phase diagram. And basically, thanks to that, we can turn off the oscillator. So we have two ways to turn off the oscillator. One is by having a high concentration of exonuclease, so you are in the off zone. And the other one is by increasing the temperature. So thanks to that, we can use the exonuclease to tune at which temperature we turn off our system. And then, of course, we can use the temperature to turn it off. The question is, once we turn off, can we turn it on again? So we did an experiment where we input some temperature profiles with some noise, quite high noise, for instance, signal to noise ratio of 2/3. And what happened is that we do low temperature, high temperature, low temperature, high temperature, and we expect, and we obtain that at low temperature, our system oscillates, then at hot temperature, it's off, oscillates again, off, on. And we did that for different concentrations of exonuclease and different off temperatures. And we found a zone where we can turn our system on and off many times. So we took these conditions for our reservoir. So to go back to where we started, so we have now a system, so a predator-prey oscillator, which we can turn on and off by using temperature. And so what we did is, so then you get the information of what is inside your system by fluorescence. So you want to know if it oscillates or not. And we use these oscillations to predict the temperature that was input. So how do we input the temperature? So we just put our tubes into a PCR machine, and that allows us to vary between high and low temperature. The fluorescence is just monitored, as I told you before, with the grass. And then for the prediction, we use a single layer perceptron predicting high or low temperature, and it uses the 40 normalized fluorescent, the last 40 normalized fluorescent levels on a window, and we move the window so that it can predict the temperature. And the result we get, so here on the left, so in red, you have the input temperature that was given to the system. In blue, you see the fluorescence that corresponds to the concentration of praise. And in green, you see the prediction. So the prediction is, I would say, pretty good, but not that good in some zones. So you see here that also we moved from high temperature to low temperature. There is a delay. And the reason is before you get the first oscillation, the system cannot, there's no way to know if you're into a hot or cold temperature. So that's something that we need to tune. We need to find a way to get a faster restart of the prey growth or more oscillation to reduce somehow this delay. So just to sum up on our work, so we were able to control a molecular reservoir using temperature as an input. We were able to tune the on-off threshold by using the concentration of an enzyme, exonuclease, and we tested it on a task that is to recover the initial input. So future work involves working with 2 oscillators to increase the expressivity of our reservoir. And also, of course, right now it's not that interesting because the last step is done in silico, but what we're aiming is everything in vitro, so is doing the classification, so using some other DNA networks that we have in the lab and connect everything. Thank you for your attention, and I'm happy to take any question.
Thank you. All right, does anybody have any questions? Don't be shy. I think everybody's a little tired.
I do have a question, maybe.
Oh, great.
Very interesting work. And you should listen to Huang's talk in a later session, who's also doing reservoir computing in the same style. So I guess I wonder, how would your system scale up? You were mentioning 2 oscillators, but how about solving a much more complicated task? How would that scale up in your setup?
So right, so in that sense, so adding our systems use very short DNA strands. So around 10 for the rabbit, 40 the fox. So in that sense, they're very concise, but because the sequences are so short, we cannot make that many orthogonal oscillators. So we are limited in that sense. So maybe for this type of oscillators, we can maybe do 3. So commonly in the lab, or what I've been able to do is 2 different oscillators oscillating in the same tube. It might be possible to add a 3rd one. Very hard. So we have other systems that are not that sharp or are not that good, but this system, it's hard to go beyond 2 or 3.
Okay, cool. Thank you. Thank you.
Great. All right, let's give Nicolas another round of applause. Thank you so much.